Welcome to when the ratio test fails. So recall, if we have a sub n, a positive sequence, if the limit as n goes to infinity of a sub n plus 1 over a sub n equals 1, then the ratio test tells us nothing. Right? So then the ratio test tells us nothing. So I have some very basic examples that we already know whether they converge or diverge for showing that the ratio test doesn't work. So for the sum from n equals 1 to infinity of 1 over n cubed, if we apply the ratio test, we have a sub n be 1 over n cubed. A sub n plus 1 would be 1 over n plus 1 cubed. So we have the limit as n goes to infinity of a sub n plus 1 over a sub n is the limit as n goes to infinity of 1 over n plus 1 cubed all over 1 over n cubed. But this is just the limit as n goes to infinity of n cubed over n plus 1 cubed. These are both cubic with leading coefficient 1. So these are both degree 3. Leading coefficient of 1. And so this limit is just equal to 1. Now, if we talk about convergence or divergence, this series is just a P series with P equals 3. So we already know that this series converges. So here is a case where the limit of this ratio a sub n plus 1 over a sub n equals 1, and we have convergence. Right? So this is a case with convergence. So a case of the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to 1, where the series converges. And now let's look at a case where we have divergence. So the sum from n equals 1 to infinity of 1 over n. This is our harmonic series. We know that this diverges. And let's see what happens with the ratio test. So for the ratio test, we have a sub n is 1 over n. We have a sub n plus 1 is 1 over n plus 1. So the limit as n goes to infinity of a sub n plus 1 over a sub n is just the limit as n goes to infinity of 1 over n plus 1 all over 1 over n. Of course, that's the same as the limit as n goes to infinity of n over n plus 1. And that is simply 1. So again, this one here is a case of the limit as n goes to infinity of a sub n plus 1 over a sub n equaling 1, where the series diverges. So here we have an example where our equaling 1 can go either way. It can either converge or diverge. We don't know which unless we use a different test. So we already knew the rule for p-series, so we used our p-series test. The harmonic series is one we know. Technically, it's also a p-series with p equals 1, so it diverges as well. So just something to watch out for if you choose to use the ratio test. It's possible that it will not do you any good, and then you'll need to use another test instead. So note in both of the above examples, we could use a different test to prove convergence or divergence. In general, if we have polynomials or if we have rational functions as our a sub n, so in general, if a sub n is a rational expression or function, so in both of the two previous cases it was, if we have a rational expression, the ratio test will most likely not work. So if a sub n is a rational expression, then the ratio test will not work. We will essentially have exactly the same thing happen as we did here. So we'll wind up simplifying to a polynomial over a polynomial of the same degree and same leading coefficient. And so we will just get a limit of 1. On the other hand, the ratio test is great for if we have exponentials or factorials involved. So on the other hand, the ratio test works really well when exponentials and or factorials are involved. So in the previous video, when we did a couple cases where the ratio test did work, both of those involved either exponential, a factorial, or both. So again, the ratio test is great with exponentials or factorials. It's not so good when we just have a rational expression for our a sub n's. So that's the ratio test. In the next set of videos, we'll be looking at the root test for convergence.